Let us start with the next part in probabilistic graphical model, that is how do we learn a probabilistic graphical model. So far we have seen, given a probabilistic graphical model structure and its conditional probability tables or factor functions, how do you do it? What does it represent? What is the meaning? How do we do inferencing in that? So all these things we have studied, and what we'll study next is that how to, given a data set or given a problem description, how do you find out or learn the graphical model. So as you can understand, there are two parts to this. The easier part is, if you know the structure of the graphical model, how do you learn the parameters of the graphical model? Parameters meaning, if you have a directed graphical model, then the parameters are nothing but the conditional probability tables, the values of the conditional probability tables. And in undirected graphical models, it would mean learning the values of the potential, the click potential functions or the factor functions. So this we call as a parameter learning problem. What we are given is, we are given a structure of the graphical model, we are given a data set, and we have to learn the parameters, which in this case of the directed graphical model is the conditional probability table. Okay, so that is the fundamental problem. In fact, if you have a discrete case, then it is very easy, because what your training data will consist of is basically a set of values. So suppose you have your training data, which looks like this. You have all those variables. You have x1, x2, x3, and x4. And you have values of them. Let's say if these are binary, then you will have training instances looking like this. Any observations? Some of the instances may occur multiple times, some of the instances may not occur at all. So you have a training set like this. And from this training set, it is very easy to find out the conditional probability table. I mean, I'll first explain in plain words. Then we will see that this can also be derived from the maximizing the log likelihood. Okay, so for example, I want to find the, so what is the probability table for x2, let's say. It will have the following terms. It has only one parent. So the parent is x1, which can take on a value either 0. So x1 can be either 0 or it can be 1. Similarly, the current variable x2, it can be either 0 or 1. So basically I have a 4×4 CPT. So this you can easily pick up. So how do you do is that look at all, so to fill up the first column, that is x1 equal to 0, you look at all rows where x1 equal to 0. So this row and this row and this row, x1 equal to 0. And out of those rows, what fraction of them has x2 also equal to 0? That is the probability. So it's just the ratio. It's the ratio of the frequencies. In how many rows x are equal to 1, x1 equal to 0 in the denominator, and in the numerator how many rows x2 equal to, let's say, 0. So that is the value for the CPT at 0, 0. Similarly, you can fill up other entries of the CPT. Note that the advantage of this undirected structure is that you only need to look at small part. For finding one CPT, you need to look at a small part of the columns. You only need to look at the parents and the present variable, nothing else. Everything else you can marginalize out. Okay, which amounts to sort of striking out other adding up over other things, and striking out for a given instance of the parent, striking out other values of this parent. So as you know that this is the factorization of a given by any graphical model. In this case, this is the factorization. So you can express the likelihood probability data given theta as the product over these factors. You can take the log likelihood, and then if you take the derivative, log becomes product becomes sum in log. If you take the derivative, so each of the parameters comes out to be just to be this frequency, what I discussed. So this way you can find. So the most likelihood solution of the parameters, most likelihood estimate of the parameters is nothing but these relative frequencies of the child given the parents from the full training data set. Okay, so you can easily derive. I am not going through it, but it's a very, very easy derivation. You just need to take the product, take the log, and take the derivative. Okay, so sometimes it may happen that you have constructed a Bayesian network and directed graphical model where you have introduced extra variables which are not observed in the training. Say you have observed only x1 and x2. x3 is some kind of hidden variable which you cannot observe, but anyway you have used it in your modeling. You have used it in your model while designing the Bayesian network. So still you can do it. Still you can write a log likelihood function. We denote it as scriptal theta, which is the log of the output y given the values of theta. And now what you do if you have given a hidden, basically this is you have to sum up this. If you find for y, you have to sum up it over all other variables x. Some of them are observed, some of them are hidden. Right. So what do we do when we have a hidden variable? We use, or a latent variable, we use the expectation maximization algorithm. So in our case, the EM algorithm intuition is as follows. So you in a training data, if you look at a row of the training data, so let's say I have a training data where I have observed x1, x2, and y. x3 is a latent variable. So these are my observed variables. And x3 is my latent variable. So what we do in the E step when you do a parameter learning in the, so suppose I want to learn the CPT for the hidden variable x3. So in the E step, or maybe y itself, not x3, y itself. All the parents of x3 are observed. So one of the parent of y is not observed. It's latent. So what we do in the E step, we sort of have a random guess about the values of the hidden variable. Initially, in the first step, we have a random guess. And then assume that to be the value of the hidden variable. You sort of estimate the other probability tables or probability tables of all the non-hidden variables, of all the other variables rather, except that variable where I have substituted. That you can easily do, because now in the training set if you have that value as if that value is there, and then you basically sum up over rest of the values, and so sort of what you have done is that in the training set you have values for only this, this, and this. Here you substitute a value. So now as if you have a full training set with x3 included. All right. So if this is so, now using this, you compute your conditional probability table as before, as I have discussed before, without hidden variable. You take the relative frequency and compute it. But now you do this over iteration in the following way. So our goal is finally to find out a conditional probability table, parameters of a conditional probability table, so that the log likelihood L theta, which is log of Py given theta, which we expand by including all other x, is log of summation over all x Py joined with x given theta. You maximize this quantity. You find out the CPTs such that this quantity is maximized. So you can easily derive the EM algorithm, which again I am not doing, following this variational lower bound and other things. And the E step just finds out Qx, which is P of x given y and the current value of theta. So given the current value of theta, you have formed a training set. So some of the variables you have not observed, but still you have counted CPT. So given that CPT may be slightly wrong because x3 I have assumed. Given the CPT, you find out P of x given y and theta. Theta is the values of this CPT. You find out. And in the M step, what you do is that you update your CPT parameters. How you update your CPT parameters? You find out, you update your theta t plus 1 as the maximum, as the theta which maximizes log of P y x theta, because this value I have in the previous iteration I have computed something. Ux also I have computed something. So using this value and whatever theta maximizes that, update your theta accordingly. Okay, update your theta accordingly. Note that finding Qx, you have already studied inferencing by message passing or whatever. Finding Qx is kind of an inference query. Find a probability of x given y and theta. So that is solved by this inference procedure. Theta is assumed to be fixed to the current value theta t. And these two steps, the E step and M step, you repeat, and you'll convert to a value of the maximum likelihood values of the conditional probability table. So here is a summary. In the complete data, no hidden variables. All the variables can be observed. It's simply calculation of frequencies. Whereas if we have a hidden variable, it's slightly more complicated. You have to first do an inferencing. You have to first do either junction tree or message passing. You have to inferencing to find out the expected counts for various settings of the given a current setting of theta t. You have to find the expected counts, and then re-estimate the parameters using these expected counts, where you replace the actual counts because you have some hidden variables by these expected counts. And expected counts are found out using this inferencing, probability inferencing, assume current value of theta, and this is done repeatedly. And this way you will convert to a result. There is an alternate formulation to this called the maximum entropy. So this is basically a maximum likelihood derivation, which EM algorithm does. And if we have there can be a slightly alternate thing. So the idea is the following. Suppose I want to find the expectation of some function f(ix) with respect to some distribution px. This is the true expectation. I can approximate it by an empirical value given a data set as follows: summation over all elements in the data set fix, because this px is naturally computed in this summation over the training data. Let's say it is alpha I. And so there may be, and this you do for every fi. This we do for every fi. So you calculate a set of alpha I. So now there may be several solutions to this. There may be several set of alpha i's which are consistent with this. What the maximum entropy problem says is that among all these choices of P possible distributions, choose the one which has the highest entropy. because it's kind of the most flexible. You can fit anything to it. So you define H as of Px, the entropy of Px, as summation over all the data sets Px log of Px, negative of that, such that this expectation is satisfied to be alpha I. Okay, and now you solve this maximization problem, and this is the solution. You usually construct a Lagrangian and take the derivatives, and you can find out P star x is some normalizing factor into exponential summation of Wi Fix. So all this you can work out, and that gives you the solution. So similarly, if you have you can also find out the probability. So there are many conditional probability tables which will be consistent with the given data, which will be which will well fit the given data. It says that find out the one, that particular CPT, which has the highest entropy, which has the most flexibility. Okay, so that is the right choice. Okay, so this frequency and all these things, these are well defined for discrete data. In general, this every node can also be continuous. Some of the nodes at least can be continuous. Then you have to apply the full Bayesian estimation procedure. So instead of frequencies, this will be the product of these distributions, and if you know that they can be Dirichlet, they can be multimonial. In general, just frequency counting would not be enough if it is not a discrete distribution. You have to, again, I am not going into these details because I have already discussed this. The usual Bayesian posterior predictive. So all this procedure you have to follow. Only thing is that the model is now defined by the factorization of the graphical model, x given parent. And in the case of if there is a hidden variable and also the variables are continuous, let's say Dirichlet or something, then you can still do your so you remember earlier we are just multiplying the prior with the likelihood to get the posterior, but now the likelihood itself is pretty complicated due to this factorization of the graphical model. But still you can do it. Still you can algebraically do it, and many interesting properties come up. And sometimes exact inference is not possible. You use approximate methods like Markov chain Monte Carlo and variational Bayes. It's just a problem. Okay, so here is a summary for parameter learning. If you have full absorbed data, no hidden variables, maximum likelihood estimate of the conditional probability table is just the relative frequencies. Whereas if you take the Bayesian, that means if you introduce a prior on the conditional probability tables, most often used when there is a continuous distribution, then you can do it using a Dirichlet model or Bayesian Dirichlet model. If you have hidden variable with discrete values, that is, it is not completely observed, you use expectation maximization for the maximum likelihood to estimate. And if you want to still go Bayesian, you have to use approximate methods like MCMC or variational Bayes. Okay, so now comes the next part. So most of the cases you will be dealing with discrete data. They are either simply frequency counting, or maybe if you have hidden variable, just an expectation maximization algorithm, which again is very simple. If you go to the slides, you will see the functional forms. You just apply them. If you really want to deal with continuous variables with a prior assumption on the CPTs, you have either a Dirichlet prior or something, then you have the derivations get more complicated. You have to use approximate methods like variational Bayes and Markov chain Monte Carlo. Okay, so now let us look at the second problem, that is finding out the structure of the graphical model. Often the set of nodes are given to you, but the directed edges or the undirected edges in the case of undirected models are not given. So what we do is that basically find out all possible graphical models given this set of nodes. So you try out all possible connections between them, all possible edges you try out, and each of them are candidate graphical models. Now you solve an optimization kind of problem to choose one among them which best fits the data. There are two approaches for this, of basically defining what is a best fit of the data. One approach says that a best fit of the data is then when the set of because moment you give a graphical model, it gives you a set of conditional independencies. It gives you an IMAP. It gives you a set of conditional independencies. And you have your training data given to you. You actually take, for example, here, this one, let's say this one. This one gives you the following factorization. This one gives you PA times PE given AD times PB times PC given B times PD given B. This is the factorization. Okay, and this will give you a set of conditional independence, like a node is independent of its non-descendants given its parents, or if they are deseparated, they are conditionally independent. So you collect all such conditional independences, and now you are given your training data. You are given your training data A, B, C, D, E. You are given a bunch of values, and you do statistical test to check whether these conditional independences hold. For example, let's say I have a conditional independence here that A is independent of D given E. A is independent of D given E, if E is observed. Or let's say I can have a conditional independence A is independent of B given E, let's say. Okay, so several such conditional independence you can systematically find out. And if you have your training set, you basically check these conditional independences holds in your training set or not. How do you check if it holds? If it is conditionally independent, then P of AB given E is P of A given E into P of B given E. Okay, and these individual things you can calculate from the probability from the training set data that is given to you, and you verify whether this relation holds or not. For all possible combination of values of A, B, and B, it's not. I mean, it's not sufficient to hold just for a single combination of values of A and B. All possible combination of values of A and B. Right, and then you can do a statistical test. They will exactly not be equal because it's a training set after all. But you can still do a statistical test and see it holds or not. So this is called a constraint based learning. The other option is to do something called a score based learning, which uses a global score, not just over individual conditional independences, but over the entire network, entire graphical model. Okay, so there are several such scores like Bayesian marginal likelihood, I am explaining them, or Bayesian information criteria. And if you look at the space of all possible such structures, each of these structure has a score, say score 1, score 2, score 3. You find out that network which maximizes this score. This is an optimization problem. Often it is solved by hill climbing. That means you have this, you try to tweak one edge, keeping all other edges constant, you remove one edge, or maybe you add one edge. Okay, and you see if the score is improving or not. The score is improving or not. If it is improving, take the new network. Take the new network. Let's say this is the new network. This is not there. This is the new network. Okay, so and then from then they are again tweak some other edge, maybe just one edge at a time. Just maybe remove this edge and compute S3 double prime. Let's say that improves even further, so you keep it. So this is the hill climbing kind of algorithm that is usually followed. But let me explain what are the kind of scores. One of the score is called a Bayesian marginal likelihood. So it is M is a model. It is nothing but log likelihood of the data given the model. You can express it as log of the integral P d given theta and m. Theta is the parameter, and times P theta given m and d theta. So so often what is done is that you assume some Dirichlet prior on the variables, the parameters given the function. You find the Dirichlet pairs, and then this is the kind of Dirichlet distribution where alpha the Dirichlet powers Dirichlet parameters, and you can compute this and you can write down your score as well. Here there is no prior. You can write a prior over models also. So maybe some models, some models which connect up this variable and this, or some variables models which have less number of nodes are preferred. So all those you can include in this prior. All right, so this is how you write down the score, a Bayesian marginal likelihood score. You have to assume some functional form, a Dirichlet prior or something. But the likelihood you can get from the data. Likelihood you can easily get from the data. So given this is a fixed network with fixed parameters, and for that how much likely is the data that you have already discussed, you can find out. It's a generative model. Okay, so once this score is found, you just follow this greedy search, this hill climbing greedy search. Okay, so you do some edge deletion, addition, or reversal. I forgot about reversal. You can do an edge reversal. And if score is greater, you keep it, accept it, and repeat. Okay, and you can similarly do more complicated things like a full Markov chain Monte Carlo on this, and still get it. Okay, so there is a even more complicated algorithm called a structural EM, even in the case when you have a hidden variable. So what the structural EM does is that usually the score is pretty intractable, very complicated. So what structural EM does is that assume a current model M, find out the map parameters theta hat using the normal EM algorithm. And then once theta hat is found and the training set is given, find the hidden variable distribution P x given D and theta hat. For a small set of candidate structures, you compute or approximately compute the score M prime, where M prime is a small set of structures. You find M prime and take their average, or not average, add them up over all the possible values of the hidden variable, weighted by their probability distribution. So you take the expectation over the hidden variables, and if the score is higher, you replace M by M prime. Okay, replace M by M prime. M prime is the best candidate structure among a small set of candidate structure obtained from M. Okay, so this way you proceed, you get the thing. Okay, so let us quickly talk about learning parameter structures and parameters in an undirected graphical model. The parameters in an undirected graphical model, as I have told you, is nothing but the factor functions, the click potentials, and there is a partition function. The partition function is often pretty complex. Okay, so in general, maximum likelihood learning of parameters is intractable. Bayesian scoring is intractable because every time you do this, every time you find the probability in the Bayesian marginal or something, you have to compute this partition function, this normalizing factor. There are many complicated solutions, many sophisticated solutions rather, which approximates this partition function z theta, the normalizing factor, or its derivative like Boltzmann machines, contrastive divergence, pseudo likelihood, or sometimes you use approximate methods like variational inference, loopy propagation, bounding methods to learn this. So learning this is more complex. Usually the parameters in a undirected models, some functional form is assumed, then from the data they are estimated. But learning a general form of gz and z theta, it's important, it's difficult. Learning a structure is even more difficult. Usually the structure is given in undirected model. Let's say an image or a speech, the structure is fixed. Okay, so this kind of brings us, but those who are interested, they can easily study these papers. It's actually very useful to learning. Learning parameters is somewhat easy, but learning structures is interesting, but very sophisticated, very complicated rather. Okay, so in summary, we come to the end of the discussion on graphical models. We studied three things. First, we studied representation. What are the syntax and semantics? What do they mean? What are the conditional independences? For that, we studied deseparation and other properties, which uses the graph structure. And we did it for undirected models, directed models, and factor graph models. And then we studied inference mechanisms. That means how do you evaluate some probabilities, probability of X given evidence E. How do you evaluate these probabilities given a graphical model along with its parameter, the conditional probability table or the factor functions. And finally, we studied a method to learn this from the data, learn either just the parameters or both the structure and the parameters. And this, in summary, this provides a very powerful and intuitive framework. You can do a lot of modeling, inferencing. When you have a large number of variables, you have some domain knowledge you can encode as a structure. You have, you can get easy insights. These are very explainable. You can easily interpret them. So these are very powerful. These are very intuitive. These are easy to construct. You have three kinds of, as I have discussed, three kinds of directed, undirected, and factor graphs. You have studied inference basically by message passing and a little bit by Markov chain Monte Carlo gift sampling. And finally, we studied how to do parameter and structure learning. There are very nice books. There is a nice course by Daphne Koller of Stanford University, excellent course. Many of my material is borrowed from there. Also, I have borrowed from Zubin Gairamani's tutorial on graphical models, also Kevin Murphy's tutorial on graphical models. And you can find many other things. There are nice textbooks. Julia Pearl has a very nice textbook about uncertainty, who is the kind of inventor of probabilistic graphical models. Even though they existed in preliminary forms, but Julia Pearl, he got his Turing Award for proposing the graphical models, probabilistic graphical models. That's an excellent book. I'd always suggest you to study that book. Okay, so there are a lot of softwares, Bezier, and most of the Python has a lot of packages to do Bayesian graphical models, probabilistic graphical models. So there are a lot of software for probabilistic graphical models. Microsoft has its own probabilistic graphical model software. Now it's not there. Earlier, Windows used to have an assistant that, do you want to do this? Some small cartoon character. If you type something in Word or something, it's kind of an assistant who tells you, do you want to write a letter or do you want? So that cartoon character was basically an graphical model, a Bayesian network over all possible things that you can do or all possible states. It's a graphical model, and there's a causality relation. You are doing this, then probably you want to do this. That's why it's a graphical model. In medical diagnosis, it is heavily used. In many modeling tasks, industrial modeling, there are many component sensors, and one contributes to the other. You build graphical models from your domain knowledge. You learn them and you use them for inference. It's very practical, very useful, very interpretable, very nice to use. A lot of software, a lot of toolbox. But it's important to know the theory behind this. And I have told you the theory, maybe often very superficially. But if we actually code it or if you use it, you will see that it's not very difficult. It's very simple frequency calculation ultimately. And but you have to take care of these factorizations and normalizations, and how do you use the conditional probability table, how do you use the structure, you have to be careful. So that's the idea. I hope some of you will use it for some practical purpose. In finance, in many places, in autonomous cars, these are heavily used. Okay, so that for more details, you can study the textbook by Daphne Koller, or you can study the textbook by Kevin Murphy. Thank you.